What is the problem of the K-means method? So last Thursday we learned about K-means. So K-means algorithm is sensitive to outliers. Since an object with an extremely large value may substantially distort the distribution of the data. So as you know, if we have a very small number, let's say I have 5 and then I have 5 million. So yeah, it is very big gap, and this extremely large value will distort or will give some noise to the distribution of the data. So there's an alternative, we call it K-Medoids. Instead of using the min, we want to use the Medoid. What is Medoid? So instead of taking the min value of the object in a cluster as a reference point, Medoids can be used, which is the most centrally located object in a cluster. So Medoid, we call Medoid, it is the same with the object. So we are going to use the object instead of using the min, or instead of using the central point or the centroid. Maybe this one is not that proper. Let's say we have this data, this, and this. So I would like to choose, for example, this one. This is the most central, the most centrally located. So it is here. So I'm going to use this one, and then we can calculate the distance between the other objects. I can calculate the distance, I can calculate the distance, I can calculate the distance, I can calculate the distance. So the same with the previous one, we can check the SSE, we can check the error. If the error is small, then okay, we can say that this object is the best or the representative. And also if we have this object, this object, this object, and this object, so we can select what is the best object to be in the central. Again, we need to check the most centrally located object. So in this case, okay, I'm going to select this one. So we can measure the distance here, the distance here, and the distance here. Oh, sorry, this is this one, the distance here. So because this is the central point. So if we return back to the example that we had before, we have 5 objects. Okay, we have our data is 5, and then k equals to 2. So I want to create 2 clusters. I want to create 2 groups. Then, yeah, if I have 1, 2, 3, 4, 5, and this one, I can select every object. Okay. So now let's say I'm choosing the object 3, and then I'm choosing the object 1. So the object 3 is chosen, and I need to measure the distance. I need to measure distance. Object 1 is chosen, and I need to measure the distance. So you know, we can calculate the error. We can get the error from this iteration. And then next, we will check if the object or the most centrally object is chosen as 4, and we have the other object is 2. Then again, we can measure the distance here, and then we can measure the distance here, and we can get the error. And then we go to the next iteration. Now we are choosing 5 as the most centrally located object, and then we select 2 as the most centrally located object. Then we can measure the distance here, and then we can calculate the distance here. So we can get the error. And so on until you find the minimum errors. Iterate until we reach the minimum distance from a Medoid in a particular case. So after you get the most minimum distance, then we will use that one as the clusters. Okay, so the idea is the same with the previous example. We can use one algorithm, we call it HUM. HUM is a typical K-Medoids algorithm. So if we have a lot of data, we have like this one, this data. So we select, let's say we have k equals to 2. Then we select this object, okay. And then we calculate what is the distance, between each of the object. Okay, we calculate the distance, and then we calculate the distance, and then we can check whether it is already good enough for the error or not, and then we can select another object. So let's say we choose this object, and then again we will measure the distance, we will measure this distance, and then if we choose another object, let's say this one, okay, then we can have another calculation, and so on until we have the least distance, until we have the minimum distance from whole iteration. So we call this is the K-Medoids clustering. We want to find the representative objects, or we call it Medoids. And we want to find the representative objects in clusters. We call the algorithm is PAM. This is partitioning around Medoids. And it has been proposed by this guy in 1987. So the idea is starts from an initial set of Medoids and iteratively replace one of the Medoids by one of the non-Medoids if it improves the total distance of the resulting cluster. So the key point is that if it improves the total distance. So as we know, we want to get the minimum, then if it goes to minimum, then we replace the Medoids with one of the non-Medoids. PAM works effectively for small data set, but does not scale well for large data set. So if when we do the calculation, we will do for every of the objects. So it says that due to the computational complexity. So if we have only 5, then maybe the iteration we will do 5 times. But if we have like 1 million or maybe 10 million objects, then we will do the iteration for 10 million. So it is too complex for getting the clustering with the K-Medoids. There's another way to improve the efficiency of PAM. PAM is the partitioning around Medoids. There's another method like Clara. Clara, it is PAM on samples. So we can select only the objects that is important, or maybe the object which is close. If it is already close with the other object, then we skip. Or There is another object, there is another algorithm, we call it Clarence. It is based on the randomized resampling. So if you know the sampling method, okay, we have the sampling like without replacement, sampling with replacement, okay, or we have the sampling, the stratified sampling, random sampling, okay. So they have another method, randomized resampling for this one. So I will not discuss in detail for those two. If you have interest, you can look at the literatures. Okay, what is the difference between K-means and K-Medoids? K-means, it is when we do K-means, we want to find, we try to find the centroid. The centroid means the center point, or it is the mean. So if we have 3 data, then we will divide with 3. So we want to get the central point, or we just say the mean. What about the K-Medoids? We try to find the representative objects. What is the representative object? It is the object that is located in the most central of the clusters. Okay. The object that is located in the most central of the clusters, then it is the representative objects. Okay, that's the difference between K-means and the K-Medoids. What is the weakness of K-means? As you might know in the explanation before, we have at least 4. The first is it works only for numerical data or continuous data. The other weakness of K-means is we need to determine the K. Okay. So we need to make the K equals to 2 or K equals to 3, K equals to 4. It is not automatic. So that's the weakness. And then K-means is sensitive to outliers. So if there is a high gap between the values, then K-means do not perform well. And then it does not group in a non-convex. Okay, you know the non-convex. We have like circle like this one, it is the convex. Non-convex may be something like this shape. Okay. So this is non-convex shape. K-means cannot do it this shape. What is the weakness of the K-Medoids? Basically, it is the same with the K-means. It works with numerical data. And then, you need to determine the K. But the proposed K-Medoids, it can be it can handle the outliers because they will select the most centrally objects. So if it is not in the central, then we can say that it is the outliers. And somehow with this K-Medoids, there is still a way to make non-convection. So that's why the 2 will be the limitation. And there is another limitation for the K-Medoids, which is it does not fit with large data set. Okay. So it is good for small data set, but it is not good for large data set. Okay. Now we are going to learn the hierarchical methods. The previous one we learned about the partitioning methods. Now we are learning about the hierarchical clustering. We need to use distance matrix. Do you remember distance matrix? We learned in the chapter 4, chapter 5. So when you use the Minkowski distance, if you use Manhattan, it is h equals to 1, then you can create the distance matrix. If you use the h equal to 2 Euclideans, you can also measure the distance, or you can use the h equal to infinite, which is a supremum. Then we can find the maximum between the 2 objects, and we can also make the distance matrix. So use the distance matrix as the clustering criteria. And this method does not require the number of cluster K. Does not require the number of cluster K. So we can just do the calculation, and you don't need to make the K. But needs a termination condition. Check what is the meaning by this termination condition. There are 2 ways. There are two main algorithms. The first is agglomerative. One algorithm is called Agnes. If we use the agglomerative, it means we use from the individual data, and then we check the distance. Okay, what about the distance of this and this? Okay, they are in the same, or they are similar. Then okay, I will group it. And then after I group this one, check what is the next smallest distance. Okay, I can see this one is the smallest distance, so I will use this one. And then okay, I check this one and C is the smallest distance, so I can group this one. And then I can see that the next step is to group all of them. So we call this is from the step 0 until the step 4, from the individual data into the group, and it is the agglomerative. The other way is divisive or diagonal. In divisive, first we make all the data in one group, and then we will measure the distance. If the distance is big, then split it. If the distance is big, then split it. If the distance, we can split, then split it, until we create the individual data like this. So the step is reverse. Agnes, it means the agglomerative nesting. That's why they call it the Agnes. And it was introduced by those 2 guys in 1990. It has been implemented in the statistical packages S+, So if you know R is the extension of the S plus. And the first implementation, they used the single link method. And they also use the dissimilarity matrix or the distance matrix. We need to merge nodes that have the least dissimilarity or the least distance, and then go on in a non-descending fashion. Non-descending fashion, it means this is ascending or from the smallest. And eventually all nodes belong to the same clusters. When we create the hierarchical clusterings, we can have a result, we call it dendrogram. Dendrogram shows how clusters are merged. So it decomposes the data objects into several levels of nested partitioning. We call it tree of clusters. So you have the tree, you have the decision tree, the decision tree about the classification. But in the clustering, we also have a tree. We call it tree of clusters. And we call in the single word, it is dendrogram. A clustering of the data objects is obtained by cutting the dendrogram at the desired level. Then its connected component forms the clusters. What does it mean? Now let's see. How many data do we have here? How many data do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. We have 9 data. Now, I want to group this data into 3 groups. Then what I can do is just set up the cutting point. So I cut this tree in this level. Then I can see that this is the connected components. So this is the cluster number 1. This is another connected components. This is the cluster number 2. And this is the another connected components. So this is the cluster number 3. This is if we want to make 3 different clusters. How about if I want to make 4 clusters? If I want to make 4 clusters, then I can cut the tree here. Then I will have, this is the first cluster. This is the second cluster. Okay, this is the third cluster, which is single data. And then this is the fourth cluster. 1, cluster 2, cluster 3, cluster 4. Okay. Diana means divisive analysis. Divisive analysis, yeah, it has been introduced by the same guy, Kaufman and Rousseau, in 1990, and it has been implemented in the statistical analysis package S plus, and now we know it as R. It is the inverse order of Agnes. So we know that if it is Agnes, then we start from the individual data. We start from the individual data, and then we group the data. This is Agnes. But if it is the divisive analysis or Diana, we inverse it. From the one big group, then we make it as an individual data. Eventually, its node forms a cluster on its own. There are some distance between clusters. As you know before, I call it singling. What is the meaning singling? Here. The Agnes use singling method. So what is the meaning by singling? Singling is the smallest distance between an element in one cluster and an element in the other. So if you want to make a good clusters, we can select the minimum. What is the meaning by this minimum? This minimum is to find the element in one cluster and another element in another cluster. So if it is the minimum, we will select it. Complete link is the largest distance between an element in one cluster and an element in the other. So I want to check the maximum, or we can say this one. This is the maximum. I want to check the largest distance. Or we can also check the average. Average distance between an element in one cluster and an element in the other. So we can just calculate the average. The other way we can calculate the centroid. The centroid, you know, in the K-means, we can calculate the centroid. Distance between the centroid of two clusters. So after I know that, we can group here, we can group here, then we can calculate the distance between the centroid. Or we can also find out the medoid, and we can measure the distance between the medoids of two clusters. So if we select this medoid, and then if we select this medoid, then we can calculate the distance between these two medoids. As you might know before, a medoid is a chosen centrally located object in the cluster. So let's get back to a simple example. In this simple example, as you might know, we need to create the distance matrix. We need to create distance matrix. How we can create the distance matrix? You already know some ways, okay? We know the Manhattan distance. We know the Euclidean distance. We know the supremum. Okay. Now I'm going to introduce another distance measure. We call it sum of square distance. What is sum of square distance? If you look at the formula on the Euclidean distance, you need to make the square root of the sigma xi minus xj square. Okay. So you are going to see every of the data, every of the attribute, and then you want to subtract it, and then the distance will be square, and after you sum all of the values, you will make the square root. But sum of square distance, you just do the summation without the square root. So we just eliminate the square root. Now let's see. I want to check the distance between 1 and 2. Between 1 and 2. Then 0.7 minus 1.0. 0.7 minus 1 power of 2 plus 0.0 minus 0.4 power of 2. So we can get the value is 0.09 plus 0.16 and the result is 0.25. So this is the distance between 1 and 2. So this is 0.25. This is the same. Why? Because we assume the distance between 1 to 2 is the same between the distance 2 to 1. Okay. 1 to 2, 2 to 1, the distance is the same. Now, for easy example, okay, because this example, it contains comma like this one. So I do not use this one, but at least you know how to get this distance matrix. So I'm going to use a new distance matrix. This is just a new one. The number is round, so it will be easier for our example. Now, you can see that we have 6 objects. How do you know we have 6? 1, 2, 3, 4, 5, 6. Okay. And I'm going to use singling. If you look at this distance, the distance from 1 to 2 is 4. The distance from 1 to 3 is 13. The distance from 1 to 4 is 24, and so on. But why this is blank? Why this is blank? Because the distance between 1 and 2 is the same with 2 and 1. Okay? So you can replace, actually this one is 4, this one is 13, this one is 34, this one is 12, this one is 8. So basically you can put the numbers like this, but just for simplicity, I will just use this triangle. Okay. Now, using the singling, select the minimum distance and group it together. So what is the minimum? Here is the distance. So what is the minimum? Let's say now we have 4, 13, we will not consider the 1 and 1 like this one, because there is no distance between its node like this. So 0 is not considered. So we have 4, 13, 24, 12, 8, 10, 32, 11, 10, 7, 3. Okay. So 3 is the minimum distance. So what is 3? 3 means this is the distance from 3 and 5. Then, since the minimum distance is between 3 and 5, we group them. 3 and 5 will be grouped. And then what we are going to do next is to renew the distance matrix. We need to renew the distance matrix. How can we renew it? Because we use the singling, it means we are going to use the minimum. What is the minimum here? So now I'm going to check what is the distance between 1 and 2. Yeah, it is still the same, which is 4. But what is the distance between 1 and 3, 5? Here, we need to select the minimum between distance 1, 3, and we need to select the distance 1, 5. the D13 means the distance between 1 and 3. D15 is the distance between 1 and 5. What is the distance 1, 3? 1, 3, it is 13. What is the distance between 1 and 5? 1 and 5, it is 12. 13 and 12, which one is the minimum? It is 12. Then we put 12 as the new distance between 1 and 3, so we put 12 here. Okay. Next, we want to check the new distance between 2 and 3, 5. Then we will check the distance 2, 3 and 2, 5. What is the distance between 2, 3? It is 10. What is the distance between 2, 5? It is 11. So what is the minimum? 10. So we put the distance 10 here, and we put the distance 2 and 3, 5 as 10. What about the, sorry, this one I think should be 6. This one should be 6. So we want to update the D6, 3, 5. It means we want to check the distance between 6, 3 and then the distance between 6, 5. What is the distance between 6, 3? 6, 3. Oh, empty. As we know that 6, 3 and 3, 6, they are the same. So we use the 3, 6, which is 9. What about 6, 5? 6, 5, oh, empty. So it is the same with 5, 6. So use 5, 6, which is 8, 5. So which one is the minimum? The minimum is 8, 5. Then we put it as the distance between 6 and 3, 5. So we put here. Okay, 3, 5, and then the distance to the 6. Let's say about this one, 4 and 3, 5. So we need to check the distance between 4 and 3. We need to check the distance between 4 and 5. 4 and 3, we have, oh, this one empty, then we will use 3 and 4. Is 7. What is 4 and 5? 4 and 5, we have 6. So we update the distance with the value of 6. So the 6 now it will be here. Okay. So what we can do next is how we can select the minimum again. What is the minimum from this matrix? The next minimum is 4. Okay. So we can group 1 and 2. So you can, because we are using the single link, so we select the minimum. Okay, so we select the 1 and 2 and we group it together, and then now we need to update again the distance matrix. Now we are going to check the distance between 1 and 2, 3, 5. What is it? We need to check 1 and 3, 1 and 5, and then we need to check 2 and 3, 2 and 5. So the minimum D13, D23, D15, D25, it will be allocated as the new distance. So let's see this one. D13. D13 is D13 is 13. D23 is 10. D15 is 12. D25 is 11. So what is the minimum? The minimum is 10. Then we'll use this 10 to update this distance between T12, 35. We use 10. And so on. So D12, 4, D13, 6, you can get this value and this value. And then we update it here, and we update it here. Okay. And then after we have this, again, we select the minimum. What is the minimum? The minimum is 6. So we can select 3, 5 and combine with 4. So 3, 4, 5 will be selected and will be grouped. After this, we can select another minimum. Now we have the minimum is 8. It is the distance from 1, 2, and 6. So we group 1, 2, 6 will be grouped, and then 3, 4, 5 will be grouped. And at the end, we can create the dendrogram. So what does it mean by this dendrogram? If you look at the numbers, okay, we have the threshold distance. So if I have the first part, 3 and 5, what is the distance? 3 and 5, what is the distance? 3 and 5, the distance is 3. So I can make the dendrogram. The dendrogram between 3 and 5, it is in the distance 3. What about 1 and 2? The distance between 1 and 2, they are grouped in the distance of 4. So this line is located in the value of 4. What about 3, 4, and 5? They are grouped with the distance of 6. So this line is in the value of 6. What about the 1, 2, and 6? 1, 2, and 6, they are grouped with the value of 8. So this is in the value of 8. And the last one, they are grouped in the value of 8.5. So we have 8.5. Now suppose I want to make the 3 groups. Or if I want to make 3 groups. So we can cut the trees. The cutting point will be maybe this one. So the cutting point, if the threshold distance is 5, this one, not this one, sorry. This one. So this is the cluster 1, this is the cluster 2, and this is the cluster 3. So the cutting point is maybe 7. So when we cut with the distance 7, then we can get 3 driven clusters. How if I want to make 4 clusters? If the cluster is 4, then I can cut here. So we can say the threshold distance is 5, and we can get the cluster 1, cluster 2, cluster 3, and the cluster 4. Okay. We can use another methods like centroid, radius, and diameter. centroid, radius, and diameter. The centroid, you know, it is from the K-Medoids. We can just calculate the middle. The radius means the square root of average distance from any point of the cluster to its centroid. So we just divide with the n, which is the number of data, and then we want to find the distance from any point to the centroid. The diameter means square root of average means square distance between all pairs of points in the cluster. So we want to check the distance between points, and then we will do the summation, and then again we divide with the number of the data. So the major weakness of the agglomerative clustering method, it can never undo what was done previously. So it is always forward. You cannot go back. And it do not scale well. So the time complexity is quite high, or n power of 2. N is the number of objects. So there's another algorithm, but I will not discuss this algorithm. If you want to learn this, you can check by yourself. Okay, explain briefly about the distance between clusters in hierarchical clustering. We have the single link, complete link, average. Okay, this is the most common distance between clusters in hierarchical clustering. And we can also use centroid, we can use K-Medoids. For numerical data set, there are 3 measures for the cluster to the centroids. What are they? You can use this one. If you use the centroid, means you will calculate based on the point, and you can check the middle. If you use the radius, it means you want to measure it is based on the centroid. But if it is using the diameter, then you will use the point and point. So those 3 measures can be used to measure based on the centroid. Okay, I guess that's all. I will explain this one in the next section. Okay, and